All right, let us begin. We're going to look at graphing and interpreting data. This is going to be for problem number 60 on page 28, related to section 1.4. We have a circumstance in which a block is being pushed with some constant force along a table that has some forces that are acting on it. However, for each of the different trials that we have, we'll have the same force, but the mass of the block will differ. Sometimes the mass is large, like in this case. Sometimes it's small. Well, we can come up with a data table to describe these different masses and the acceleration, or the rate at which they change their velocity, that can be observed, and we can chart the two. So in order to make a data table, we need some first variable. That first variable can be mass, described in kilograms. And then we need some second variable. The second variable here that we're looking at is acceleration. That's measured in meters per second squared. Here's our data table. The first block that was used is 1 kilogram, 1.0 kilograms. And the acceleration that was measured when this block that weighs 1 kilogram was pushed with a constant force, whatever that force was, the acceleration that was measured was 12.0 meters per second squared. Now, because I put kilograms in this column, all I need to do is record the number. I actually don't need to show the unit of measurement because that's noted here. So I also don't need to do the same for acceleration. I saw that if I put a 2.0 kilogram block, the acceleration is 5.9 meters per second squared. If I have a 3.0 kilogram block, so I keep adding heavier and heavier blocks, look what's happening to my acceleration. My acceleration, it looks like, is getting smaller. So finally I'm going to stop at a block that has a mass of 5.0 kilograms, and we see an acceleration of 2.50. All right, so here's our data table. Here's the information that we can put into a visual medium, that being our graph. And then we can interpret the graph. We can already see that as we increase mass, so I can see that as mass increases, as mass gets larger, what's happening to acceleration? Acceleration is getting smaller. The acceleration is lowering. In other words, there's an inverse relationship. I can already see that from the data table. As this gets larger, these values get smaller. Inverse relationship. Mass goes up, acceleration goes down. I should be able to see that visually in a graph. Put that in a graph. So I still have my data right there. Draw a graph to describe this data. I have on my independent variable axis, which is my x-axis, that is my mass. My independent variable, the variable that I'm changing, is mass measured in what units? In kilograms. My dependent variable, right, so I can even write that here. Here's my independent variable. This is my independent variable. My dependent variable is up here, and that is what's responding or depending upon the fact that this variable is changing. That's my acceleration. I'm just going to put ACC, and that's measured in meters per second squared. All right. Now I need my tick marks here. 1, 2, 3, 4, 5 for 1 kilogram, 2, 3, 4, 5. And then my acceleration. I'll do even smaller tick marks here. It doesn't have to be 1-to-1. I can do every tick mark being 2 for a different axis. That should be 8. Should be 10, 12, 14, 16, 18, 20. When I have a 1 kilogram mass block that's pushed with a constant force, the acceleration that's measured is 12.0 meters per second squared. For every 1 kilogram, or if I'm pushing a 1 kilogram block, there's my acceleration. What if it's 2? Now I'm at 5.9. Okay. It's 2 kilograms, then I go up to 5.9, which is here, right? Almost 6. It's 3, 4.1. Okay, there's 3. 4.1 is right about here, just a little bit above 4. What about if it's a 4 kilogram block that's being pushed? If it's 4, then I'm at 3, which is midway in between 4 and 2. What about 5? 2.5, which would be just a little bit above the 2 tick mark. What sort of graph are we observing here? We see that is actually an inverse graph, right? It's this downward sloping. It's getting smaller and smaller, closer and closer to an acceleration of what? Of an acceleration of 0. So say if my mass is really, really large. If I have a large mass, then that tells me I'm going to have a very small acceleration. Small acceleration. Now that we have this data table confirming our suspicion about an inverse relationship, we see the visual inverse relationship, right? As 1 gets bigger, as mass gets larger, acceleration gets smaller. It's not quite a straight line though, right? There's a little bit of a curve here. So it's something like what we see in math. It doesn't look like this. Y equals mx plus b. What's an example of that? Would be something like y equals 2x plus 2, right? That would be a straight line. This is not a straight line though. Instead, this is more like the graph of y equals 1 over x, right? Y equals 1 over x, which has this sort of relationship to it, right? Has this sort of inverse curve. By inverse, we just mean one goes up, the other goes down, the other variable goes down. Now, because we see that this is an inverse, then we can use this equation, this is our inverse equation, to describe this relationship. So not only do we see a descriptive relationship that we just offered, which is saying inverse, but now I can mathematically define it. I can say that my y value, which is what's on my y-axis, acceleration, so I can write that acceleration is equal to 1 over, what is my independent variable, my x value? Mass. Or maybe put more simply, a for acceleration equals 1 over m, representing mass. Where a is the same thing as y, right? It's whatever's on my y-axis. That's the measurement that's on my y-axis. And m, standing for mass, is whatever is on my x-axis, my dependent or independent variable. So this is the equation that describes this right here. This is the equation that describes the relationship between acceleration and mass. Now what we see is that it's not always just equal to 1 though. So this is a particular case of an inverse relationship. The more general case, I'll take it over here, the more general case is y equals c, some constant, over x. Some constant. The question is, what is that constant? Or maybe it's 1. In the particular case, we have y equals 1 over x. In the general case, we have y equals some constant c over x. Okay, we can do a little bit of investigation to find out. So we see that if we take, now we can take one of our data points all the way from up here. We take one of our data points, say we take 3. So if 3 is our mass, and then we put it back into our equation here. So now we have some constant c over a mass of 3.0. That gives us an acceleration of 4.1. 4.1. So our constant, at least using just one of those data points, our constant must be what? Well, we have to solve for it. How do we solve this equation? Well, we need to get rid of this denominator here, right? Because we want to get c by himself. In order to do that, we have to do the opposite to this side of the equation of what the 3 is doing to him. We need to get this 3 away. Right now, the 3 is dividing c, so that means we need to multiply by 3, right? Multiply. Well, if we do that to one side of the equation, we have to do that to the other in order to maintain this equal, right? This equality. So that means we have to also multiply this left side by 3. Now what we're left with is these. See how we have numerator and denominator? These guys cancel. They're the same. So we're left with just c on the right side. What do we have on the left side? We have 4.1 times 3.1. And that is going to be our c value. Whatever 4.1 times 3.1 is, that's our value of c that we can then put back in this equation over here. So that means actually our equation is a, our acceleration, is described by c. What's our c value? What did we find it to be? 3.0 times 4.1, whatever that is, over whatever the mass is. I can check that. We can put one of these values up here into our equation and see if that matches up. So if we put one of these values from our table in there, so say if we take this next one, 4 and 3.0. So if we put 4 in for the mass, so 3.0, that constant always stays the same for this relationship. If we put 4.0 in for our mass, what will we get in for the acceleration? We'll get something really close to 3, right? 3 times 4.1 is about 12, right? A little bit over 12, divided by 4. We'll get something very close to 3. Now remember, as part of this problem, we have, why is it not perfectly 3? Because we have some friction, some other forces that aren't accounted for. This is not a perfect relationship. This is a relationship that very closely, or best fits, right? This is a best fit line that best fits our data. Not perfectly, but best fits it. All right, so quickly recapping from our data table, we were able to put that into a graphical relationship to see that yes, indeed it is an inverse. We know that it's not a linear relationship. That's what this would be. It is instead an inverse relationship. This is a particular form of inverse relationship, y equals 1 over x. The more general form is y equals c, whatever that constant might be, over x. We need to find what that constant is by putting in a y value and an x value. That's what we did down here. We put in a y and an x value. We said the y value, 4.1 meters per second squared. The x value, which was our the x value, which was 3.0 for the mass, solved for c using just some simple algebra. Our c is 3.0 times 4.1, whatever that is, right? And then we put that into our general equation. Here is our general equation right here that describes as a best fit what is going on in here. So that we could, say if we had needed to find, well, if the mass was 6.0, what would be the acceleration? We could find that out. We just need to use our equation that we have down here. So using our equation, I'm going to rewrite it back up here. Our equation of A equals 3.0 times 4.1 over m, the mass. All right, well, I can find what A is. C stays the same, right? That's part of this relationship. What's the m? 6.0. So it's probably going to be something, what does it look like? Well, 3 times 4.1 is a little bit more than 12. 12 divided by 6 is going to be 2. So it should be just a little over 2. Something close to, I'm going to say probably 2.1 if I throw that in my calculator. Does that number make sense? Well, look, we increased the mass from 5 to 6. What had we seen happening in this relationship as we increase mass? We saw a decrease in acceleration. We were at 2.5. We increased the mass. Our acceleration should get smaller. Our acceleration does get smaller. So this mathematical relationship that we were able to define, to discover, is a good approximation, a best fit for the data that we have. All right.